Okay, so now we're going to look at some, I just want to finish off this Laplacian step and then we can get to the clustering part and how this actually shows up. So you can do a few things with the Laplacian and we'll see that one of the approaches is to normalize it, just like we normalize the adjacency matrix. So the first one is, this should be pretty clear, right? So you take the Laplacian matrix and if you divide by the degree, every row divided by the degree, you can write that as delta inverse L, and that gives you a normalized Laplacian matrix. But this one is a little bit more interesting because it looks a bit weird. This is also doing a normalization but in a different way. Okay, what this is doing is, instead of dividing by the degree of each row, of each vertex, and this makes the matrix not a symmetric matrix, right? It's an asymmetric matrix. There's a symmetric way of doing it. So we call this a symmetric Laplacian. So what you do is you actually take, in some sense, half of the degree, or the root rather, right? So if you just do delta inverse half times delta inverse half, you get delta inverse. Right? It's like the root. So when I say half, it's the root of the degree. So this delta inverse half is just this matrix, which is essentially 1 over root d1, 1 over root d2, and so on. So this, actually, let me write it down in a separate page. So delta half, root delta or delta half is simply root d1, root d2, root d1. Okay, that's called the root of the degree matrix, and the inverse of the root is again pretty much simple. So when I say delta minus half is actually 1 over root d1, 1 over root d2, 1 over root d. So this is what we mean by the two things. And of course we know that delta half times delta half is actually going to be delta inverse. So what we did is we took the inverse and split it into the roots, and when you multiply them, you get the inverse back. So this, as I said, this is just a different way of normalizing. So what you do is you put the Laplacian in the middle, and you multiply on the left and the right by the inverse root of the degree matrix. So ultimately, this is probably interesting to look at. So what it boils down to is that what you're doing is you're taking the actual entries, like the degree entries except for the self transitions, and you're dividing by d11, root of d1 times d1, root of d1 times d2, and so on. And this is d2 times d1, but d2 times d1 is the same as d1 d2, so they turn out to be symmetric entries. So this is a way of normalizing by the degree, but also keeping the matrix a symmetric matrix. And the good thing about these two matrices is that both of them actually are positive semi-definite. So they keep the properties of the Laplacian. So even after normalizing, okay, this is clearly positive semi-definite. This matrix, even though it is not symmetric, okay, it still has real and non-negative eigenvalues. It has exactly the same eigenvalues as this one. So the good thing is that these two matrices share the same eigenvalues. The eigenvectors are slightly different. But the eigenvalues are exactly the same. One can actually prove that every eigenvalue of this is an eigenvalue of this, and vice versa. So these two are so they are positive semi-definite in that sense that all the eigenvalues are not negative. All right, so that's that. So let's basically, this is the symmetric one, and you can look at the. We'll do this in the hands-on part. So we'll actually go through some of these matrices and try to look at them at that point. Okay, so now that we have all this, we might be, as I said, where does the connection between cut and the matrix show up? Okay, so that's the part of this lecture, to figure out how to actually connect these two ideas. Okay, so here's the point now. So the goal, like I said, in graph clustering or graph partitioning is that given a graph, we want to find these k clusters, okay? Cluster number 1, cluster number 2, cluster number k. And this is going to be a partitioning or a splitting of the graph into k parts. Now, any kind of split you do, let's assume that you have two subsets of vertices, okay? So S is some set of vertices, T is some set of vertices. They could be the same, they could be different, they can overlap, doesn't really matter. This function can be defined for any two subsets of vertices. All this says is what is the, if I have S and T, this just says what is the similarity value that where one endpoint is in S, the other endpoint is in T. Okay, so I'm looking for all the edges between S and T, okay? And I'm looking at the weights of the similarities for the edges between S and T. Okay, that's the basic understanding of this big W. So the weight function basically says what is the weight where one vertex I take from S, one from S, one from T, and I add them all up. Okay, all such pairs. Okay, so that will be the. So in other words, if you have a network, you got a bunch of vertices here, a bunch of vertices here. This is S, this is T. So these will be all the edges that are connecting them. Where one point is here, the other point is there, and what is the weight of that? Aij. So we just add all such pairs. So just only those vertices that are in that cut, so to speak. Okay, so one endpoint in one, the other endpoint in the other. All right. So we'll see that this is going to play obviously a key role. So let me start with the with a sort of an example first. So what I'm going to do is I'm going to say that so you're given a graph G, and your goal is to basically take that and let's say partition into three parts. Okay, so C1, C2, C3. So I'm just going to say let's say K is equal to 3 for example. So in this case, K is equal to 3. Now, what should your objective function be? So first of all, if you're going to do clustering, there should be some objective function that you want to sort of either maximize or minimize. So in this case, we want to minimize. We want to, right, because every edge is a similarity. So it will be, when you cut something, you want to minimize the similarity. So here's the function that I can think of. Okay? It's called the ratio cut. Ratio cut objective. So the ratio cut objective basically says, okay, let's look at each cluster, and let's look at the complement of that cluster. The complement is everyone else that is not part of my cluster, and let's look at all the edges that cross over from one cluster to everyone else. So if I pick C1, okay, the complement of C1, so C1 is a cluster, and the complement of C1 would be everyone else. It will be C2 union C3. Okay? So it's basically one cluster against every other cluster in the graph. And what I want to do is I want to minimize the cut between C1 and the complement of C1. Okay, so that will be our function. C1 complement of C1. So that should be one of the terms in my objective function. But actually every cluster should be doing the same thing. C2 should be looking at itself and it tries to minimize the cut with respect to everyone else. C3 should be saying the same thing, okay? With me versus everyone else, I want to minimize. So let's add all these things together. And that gives me my ratio cut objective, or at least one of the components of that. I'm going to say let's minimize. So let's minimize over all possible clusterings. Okay, so I'm going to use this fancy C. So fancy C is this clustering, C1, C2, C3. So among all the different ways that I can actually partition, because I don't know which is the right way, right? We have to discover that. Among all the different ways of partitioning, this is what I really want to. So that's why it's called minimum over C. I want to minimize this sum, Ci complement. Okay, that makes sense. That means my similarity to everyone else is being minimized essentially. and every cluster is saying the same thing, minimize with respect to everyone else. Okay, so this is fine, but this has a little bit of an issue, the issue of balance. Okay, so there is no balancing term. So you'll end up, with picking one vertex and another vertex. Okay, those will become the two clusters, and the rest of the graph will be the third cluster. So these two single vertices are of no use to us in terms of clustering. So we have to have a balance condition. So the balance condition I'm going to do is a very natural one. The larger the cluster size, the better, right? Now, because it's a maximization issue, I want to have a single, objective, not a max-min. I just want to have a minimization problem. So what I'm going to do is I'm going to say, if you want a large size, the value of the objective should be smaller. Okay? So the larger the size, the smaller should the objective be, because you want large clusters. So the best way to do that is actually to divide by the size of the cluster. Okay, so cardinality of the cluster. This vertical bar here denotes the size of the cluster. How many vertices are in that cluster? So now this makes sense. So basically, you want large clusters. Large clusters will result in smaller objective values, which is what you want. You want to minimize. So there's only one. So this is actually called the ratio objective measure. Okay, so this is a ratio objective. There's another objective called the normalized objective. So let me describe the normalized objective. So the normalized objective is pretty much the same. So this is a ratio objective. Ratio cut. And there is this second one called the normalized. It is also a minimization over all clusterings, sigma, and the top part doesn't change. It is actually the same. So you start out with the same assumption that I want to basically minimize the similarity to everyone else. Every cluster does the same thing. But whereas this one actually looks at only the size, what you really want to look at not only the size but also the weight. Right? So this is ignoring, this one cluster may have lots and lots of nodes, but the weights may be very small. Not only the size matters, but also the weight on those edges matters. So how can we use the weights on those edges? So we use this new term called the volume. Volume of Ci. Now the volume of Ci, let me define that, is basically the sum of the weight from Ci to everyone else, including itself. So it's basically the volume of Ci. The volume of Ci is defined as basically the cut between Ci and everyone else. Okay, V is the set of all the vertices. So technically speaking, I could have written it in this way. It's actually the volume of Ci with respect to Ci plus the volume of Ci with respect to Ci completely. It's the same thing. Internal weights and external weights. You just want that cluster to be a weighty cluster. Okay, whether it's internal or external doesn't matter. So that's the basic. Obviously, you want the internal weights to be higher, but the objective will take care of that. Okay, those are the similarities. And so the more the volume, the more the WCI term, the better off. Because you're anyway trying to minimize this part, right? So that means the higher the volume means that the internal weights are really high. So it will automatically take care of that as part of the objective. So this is called the normalized objective measure. Or normalized cut. Okay, so, and there are some other, you can do many other things, but let's just start with these two. And now I'm going to show you the connection between the objective and the matrix. Because right now it's not clear where the matrix shows up. Okay, for this we have to do a little bit of, I have to do a few sort of tricks to make this happen. So let me show you some, how to tie the graph to the linear algebra. So let's see how we can be doing that. Okay. So first of all, look at the clustering, right? So clustering, you either belong to a cluster or you don't belong to a cluster, right? So it's like a binary vector, 0, 1 vector. So basically I can write it this way, that for every cluster I, okay, there is a corresponding vector Ci that basically says 1 or a 0, 1 or a 0, 0, 1, 1. And what does that mean? That means, so let's take a small example with just two clusters. So let's just say that these belong to cluster 1 and these two belong to cluster 2. Okay? So what would be the cluster, I call this the cluster indicator vector. Okay? So this C1, so this is the cluster indicator vector. So for example, C1 vector will be a vector of 5, it's of size n, okay, because there are n vertices. So in this case it will be 5. And it will be basically, so let's just number them, 1, 2, 3. Actually, let's number them a different way. Let's say 1, 2, 3, 4, 5. So what this will say is, okay, cluster 1, which vertices belong to cluster 1? It's 1, 3, and 4, right? So it will be 1, 0, 1, 1, 0. And C2 will be the opposite. It will be 0, 1, 0, 0, 1. Right? So this is just an indication. That just says, for every cluster there is a binary vector that says, does a node belong to that cluster or not? But we think of them as now a vector. So this is the sort of one tile. So now let me tell you another interesting thing. So if I want to know the size of the cluster, how can I get the size of the cluster? Because this is a binary vector, you can of course count them, but I want a matrix operation for that. Okay. So how do I get the size by a matrix operation? You can do a dot product. Dot products, you can do basically C1 transpose C1, yeah, or C1 dot C1 will give you basically 1 times 1, 0 times 0, 1 times 1, so it actually give you 3. So the dot product tells you the size of the cluster. And so I'm going to write this also, we write this as C1, C1 square. So this is actually also called the square of the magnitude. Okay? So the magnitude of a vector is basically the root of the dot product. So this is just the square of the magnitude of the length of the vector. So in other words, this term that we have, let me just quickly go back here. When you talk about the length, the size of the cluster is nothing but the cluster indicator vector square with the length square. So I can actually say the size of the cluster is actually denoted this way, is actually the same as Ci squared, which is equal to Ci transpose Ci. So I'm misusing my notation here because it's hard to, but I'm using the following notation that, without the arrow is the cluster, and with the arrow is the indicator vector, right? So it might get a bit confusing when I write it out, but just think of, if I'm talking about vectors, it is just a binary vector. If I'm talking about a cluster, it's just a set, which points belong to that set. Okay, so we have one connection now that at least, so the idea is to link those, objectives to the vector operation, and then the matrices will then emerge from that. So we're able to link the sides to some operation on some vector. Okay, but now what about the weight from what about the volume? Volume from Ci to V. How can we write this expression? Right. So what was this expression? This was basically W Ci to V I'm sorry, this is just the volume of Ci. So I want to now come up with the vector, expression for this one. So this one, what is it basically saying? It's saying that take every vertex in Ci, right, and compute the similarity to everyone else, to all other vertices, internal or external, that are within the cluster or outside the cluster. So if you expand this out, this would be the sum, right? It should be the sum over all points x, okay, belonging to Ci, and this is going to be it is just going to be, in fact, the degree of x. Is that true? Let's think about this. So, because this is the weight, right? And weight is what? The weight is the sum. So actually, if I were to expand it the other way around, it is actually the sum of all x belonging to Ci, sum of all y belonging to V, right? A, x, y, right? All the weights, all the similarities from x to everyone else. Well, but each one of those, right, when I say x to y, it's actually the degree of x, right? Because sum over all y. So that's, in fact, a little bit in a compact notation as well. Okay, we're not done yet. What I want to do is I want to get rid of this x belongs to Ci. Because, this is sort of an operation that I cannot do using just a matrix. So I want to do a sum over all the vertices. So how can I do that? I can use the indicator vector. Because the indicator vector tells me which point belongs. So if it's a 0, it will automatically drop out. If it's a 1, it will count. So this actually I can write in this manner. It's actually the sum over all points, not just, it's sum over all vertices j, and this would be the cluster indication for the ith cluster. So it will be ij dx, or rather dj. So let me just use x actually. So if I do this, do I change the value? Now I'm summing over all x, right? Here it was summing only over the points that belong to the cluster. But now if I sum over all x, the x entry of the indication, of the indicator vector will be 1 if and only if x actually belongs to that cluster. It will be 0 otherwise. So in fact, this sum and this sum is exactly the same. There's no difference. One is taken over the whole thing, but those members that do not belong will be automatically 0. And this one obviously assumes that I'm only summing over the points that belong to the cluster. So anyway, this is something you can verify. But long story short, this can actually be written as a very neat formula. It's actually just this times the degree matrix times Ci transpose. It's a quadratic sum. It's a quadratic sum which involves a degree matrix. Okay, so multiply on the left and multiply on the right, that makes it the quadratic summation. And because it's a diagonal matrix, basically you'll get exactly the same term back. So this is something that we want to basically keep in mind. This is interesting. This is going to help us. So the volume is basically simply the cluster indicator vector. Now this is just one vector times the degree matrix times that same vector. Okay, but of course you have to transpose on the left to make the quadratic sum. So now we have two parts fixed. So then we only need the third part. So the third part is, what about W Ci to Ci bar? How can I link this to some matrix? So this one, if you think about it, this I can write in the following sense. It's actually the weight from Ci to V minus the weight from Ci to itself. Right? So it's basically all the weight to everyone else, but subtract the internal part, then you'll get the external part. And this one I've already showed you what that is. It's exactly the same as the volume. Right? So I can just borrow this. So this is simply Ci transpose delta Ci. But what about this part? Well, this part, if you just think about it for a minute, it's actually just using the adjacency matrix, okay? And the adjacency matrix, only the internal parts have to be kept. So this can be written actually as Ci transpose A Ci. Okay, so I'm not going to go into the details here, but you can verify that this is true. So now, what does this give me? This gives me, you have the same vector on the left and the right, so I can actually pull it out, and I get delta minus A Ci. And this is nothing but the Laplacian. So now we have tied our objective to actually the Laplacian. So this is sort of the series of steps we did to tie up with that. So now we have a matrix operation that we can do. So now let's write down the matrix objective. So the matrix objective is, so the ratio objective, the ratio cut is simply going to be minimize I goes from 1 through k. Okay, it will be Ci transpose LCi divided by Ci squared, and the normalized cut is going to be minimized from I goes from 1 through k. The top part is the same, but the bottom part is this is the volume. So that's the only difference between these two objectives, is what are you dividing by, and here is just the Laplacian. So let me tell you what the upshot is, right? Here basically the Laplacian shows up, right? Here it is what? It is Laplacian by the degree matrix, right? So it's actually the normalized version has to be there. So when you actually solve this equation, it turns out that there are two ways of solving it. You can either do delta inverse L, right? So whenever you have two matrices and you're dividing one by the other, it's kind of like delta inverse L, or you can do the symmetric part. You can do delta minus half L, delta minus half. So that's where the, so basically you can solve this by using the Laplacian eigenvalues. So in fact, this is a standard matrix algebra result that to solve this problem, if you want to find out the minimized, the minimum value, all you have to do is take the Laplacian matrix, compute the k smallest eigenvalues, okay, and if you add them up, that's the value of the objective. So the eigenvalues tell you the least value of this objective. So that means you know now that I can, what is the minimum possible value you can obtain, and it is simply by taking the eigenvalues of that Laplacian. And here, if you want to solve this one, you can do it, like I said, in two ways. So you can take this L over delta. Now I'm actually simplifying things because this is not exactly what you can do. You have to do a little bit of manipulation, but ultimately it boils down to, this expression can be done in two ways. You can either do the LA, which is delta inverse L, the asymmetric part, and you compute the eigenvalues of this one, or you can do the Laplacian symmetric, which is delta half L, delta half. Okay, so you need to compute the eigenvalues for this one. Actually, the eigenvalues for both are the same, but the eigenvectors will be different. So we now know that we can actually optimize these. These are optimal values, okay? So these are optimal values for that objective. But I skipped one crucial thing. The crucial thing is that here, to get the optimal value, you have to relax the condition that the indicator vector is a binary vector. Okay? So let me sort of backtrack, because this is a bit confusing, because I'm sort of talking more about the eigenvalues, but here's the issue. Supposing you say you want to minimize the ratio cut. Okay, so you say Ci has to be binary. And now you want to minimize, right? So you want to say, okay, Ci transpose LCI by the magnitude of CI squared. Okay, unfortunately, this is an optimization problem, right? So you have to find me, what do you have to find? And this, by the way, is now these vectors you have to find me. C1, the C1 vector, the C2 vector, the CK vector. So that's what's unknown. So I do not know the indications, right? I do not know which point belongs to which. So these are all the possible binary vectors. You have to find the least value of this objective. The problem is that this becomes a constrained optimization problem because we know now that yes, these guys can only be binary. So this has to be a constrained binary indicator, right? Or rather constrained optimization problem. Okay, let me tell you, unfortunately this problem is NP-hard. You cannot solve this in polynomial time optimally. Because the problem is the binary constraint. The 0-1 constraint basically destroys any hope of finding a solution. So what we do is, we say let's relax that condition. Right? So since I cannot really give you a binary vector, which is what you really want. You want a binary value, but let's just pretend for the time being that I don't really care. It doesn't have to be binary. Maybe later on I can do some tricks to find it out. So let's just make Ci to be any real vector. So it can take on any value, positive, negative, whatever, right? So we make this relaxation. So because this problem is an NP-hard problem, so what we do is we say, okay, we're not going to solve this problem, but we'll solve some other simpler problem, but we'll solve it optimally. Okay, so we'll say, okay, so we'll say relax the constraint. And what that means is allow Ci to be any real vector. That is, it will belong to Rn. Okay, a vector in the real space with n dimensions, because there are n points. So it's just a vector of length n. Now if you make this assumption, it turns out that this objective can be actually solved in an optimal manner. So you can get an optimal solution to a relaxed problem, not the problem you wanted to solve, to some other problem. So now this eigenvalue, eigenvector stuff, because remember, eigenvector, the entries of the eigenvector are not constrained to be binary. Right? They can be any value, whatever it converges to, it will be that value. So that's the point, that when I was talking about solving this, I was talking about the relaxed version of the problem. Okay, so now you have this kind of a dilemma. You wanted to solve one thing, okay, that's NP-hard, so you said let's do something else, and now you find an optimal solution. So now I can do, for example, for the ratio cuts, the solution. So let me tell you the solution. The solution is to find the k smallest eigenvalues and the corresponding eigenvectors of L. And then for the normalized cuts, you just replace this with either LA or LS, the normalized. Okay, so this is all there is to it, right? But what have you done? I mean, you have found something which is optimal. So this is actually optimal solution. But it's optimal for this problem. It's not optimal for the binary problem. So, and unfortunately, there is no theory, okay, that links those two. So, you have solved something optimally, but there is no relationship actually with the binary solution. I mean, there is no easy solution in any case. Right now, there is no known relationship between, I mean, except for maybe some toy graphs, you can look at the relationship. But in general, there is no connection between the Ci you find in the real space and the binary vectors. So then you say, why are you even doing all this, right? But it turns out that this brings me back to that notion I had mentioned before, the notion of embedding the graph in a space. Okay? So what you're actually doing here is, the rationale is, and this is actually the key rationale that you can think of. You're saying you start out with a graph, okay? Now from this graph you compute the Laplacian, the symmetric Laplacian, the asymmetric Laplacian, whatever, one of those things, you compute the eigenvalues. So what you're trying to do is, you're trying to compute these vectors. So I'm going to say, there is a lambda lambda n, there's a lambda n minus 1, lambda n, the k smallest eigenvalues. So these are the k smallest eigenvalues. But then for each one of them there is a corresponding eigenvector. un minus 1. So there are the k eigenvectors. Now what we are actually saying is that you are taking the graph and you're embedding it into the space. Every eigenvector defines a new direction. And we can prove in this case that they are all orthogonal to each other. That means they actually make up a coordinate reference system. So it's like saying that if I had three, if for example for k equal to 3, you pick up the three smallest eigenvectors. So make the first one, your direction, your one direction, so that would be your x direction. So this would be u3, or rather, so I'm sorry, it will be un minus 1 and un minus 2. Okay? So this kind of acts like the x-axis, this is like the y-axis, this is like the z-axis. So each one of these eigenvectors is actually defining a direction, and every point has a value for one of these, because each of these vectors is of length n. So it's like saying that you're taking a node of the graph and you're mapping it in the space. Okay, what are the coordinates in the first, second, and third? What are the values? Okay. So you get mapping into this space. Another point that might be closed, you hope that it will land up in that, in that space, and stuff like that. So if you had a graph like this, which was 1, 2, 3, 4, 5. So then 1 and 2, and maybe 3 land up here, and then maybe 4 and 5 land up here. So in this space now you get points. So basically the graph has been turned into a regular coordinate set of points, and now I can apply all kinds of clustering techniques. But the hope is that because you did this transformation, it's much easier to separate them in the space, and what you might end up doing is just run like a k-means type of a clustering algorithm. Basically you can apply any simple clustering algorithm and it should be able to, let's say, divide them up. So let's say these three belong together, these three belong together. So it's very easy to separate. So the hope is that, yes, there is no theory. Okay, I cannot guarantee that you'll find the right solution in the binary sense, but you've done something optimal in a relaxed space that lets you map the graph into a coordinate system, and then in this coordinate system, it's easy to separate. Hopefully it's easy to separate the points into these groups. So that's basically the point of, so this essentially acts like a graph embedding. And so that essentially is what spectral clustering is all about. Basically taking a graph, mapping into this new eigenvector space, and then using your standard notions from there.
Sir,
yeah.
If all these values will be equal, suppose as 0, then what will be able?
That's a good question. The smallest one is 0, we know that.
The smallest may be 0.
The smallest is 0. The smallest is always 0.
And there may be more than one.
There could be more than one possibly. That is, normally what you should do in that case, I think you should try to pick up the non-zero ones. Because normally although I take that back actually. sometimes the number of zero eigenvalues, okay, this is actually a fact. The number of zero eigenvalues corresponds to the number of connected components. So if you take a Laplacian matrix, okay, and you look at how many eigenvalues are zero, it's actually the number of connected components of the network. So in fact, what that means is that those are anyway going to be isolated. So you just pick each one is going to be a different cluster. Now you might have one large cluster which might still need further dividing, but the number of zero values can actually help you, figure out the cluster. So this I can state it here that the number of zero eigenvalues corresponds to number of connected components. Rather of L. Okay. So this is a well-known result in matrix theory. So actually, but this is a very good question because a lot of the time you can actually analyze the what is known as the spectrum. Okay. So if you look at the eigenvalues and you see if you somehow plot them, okay, so how many of this kind and what the values are. So this plot is called the spectrum plot. And there is some, so one can learn a few things from that spectrum plot. So if you have some very high and then a lot of them are very low, that means it's very high at capturing a lot of the information, and that can be used for the clustering and other things. So yeah, the spectrum actually helps you understand the structure of the graph. Okay, so this is pretty much what's here in the slide is I've just written it out. So this is just saying the same thing over and over again. But I just wanted to work it out. So basically here's the spectral clustering algorithm. If you want to know how to take a graph, all this says is, if you have the graph, fine, right? Otherwise just compute a similarity matrix. And then depending on which objective you want to choose, ratio cut or normalized cut, either choose the Laplacian or choose the symmetric or the asymmetric Laplacian. Okay, so that's my matrix B. And now find out all the eigenvalues and eigenvectors. Actually, not all. Just find the k smallest eigenvalues and eigenvectors for the B matrix. So B can be either L or any one of those other Laplacians. And then you get this new space. Okay, this is your eigenvector. So sort the eigenvalues. The smallest is n, the next one, the next one. Take these eigenvectors, and they basically become essentially this becomes like a new data set. Right? This matrix U is an n by k matrix. Right? This is the point I wanted to sort of say here. That this matrix U is simply an n by k matrix. So the matrix U. So in other words, it has actually n rows and k columns. Right? So this is basically column 1, column 2, column k, point 1, point 2, point n. So it's as if you've taken the graph, right? So each point in the graph has been mapped to a k-dimensional space. The row corresponds to a point in k dimensions. And that's basically, now you apply k-means and you detect the clusters using it. So this is called the spectral clustering algorithm for clustering a graph into k parts. Okay, so that's one approach. Yeah. Oh yeah, that it sometimes helps, it sometimes doesn't help. So this is because people published papers one way, some did the other way, and so they say that if you are using, so this usually helps only if you are doing the symmetric Laplacian, because the symmetric Laplacian, what happens is you're dividing by the the root of the degrees from two different parts. So somehow they said that if you normalize, they get better results. So it's pretty much an empirical thing. So it's not really, there's no theory why you should do it. So that's why I just keep it here that you can technically just normalize the rows to be unit vectors, but it's not a necessary step. So the main intuition is that you're basically mapping it onto a k-dimensional space, and then you're clustering in that k-dimensional space. So this normalization is just something extra you can do. That once you map the points, you can map them all to be unit vectors. Right? It's like any other transformation for any other data set you might want to do. but that's not really the key. It may or may not help. So actually in this small example, this is, I wanted to find two clusters, and so, this was the two smallest ones. This is the smallest direction, the second smallest direction. And when you look at the graph and you plot it, in this embedding, it turns out that 1 and 3, 1 and 3 and 4 and 2, they belong to this part. I mean, so, this line is not there. These points are here, and 5, 6, and 7 end up here. And so, what you've done is you've sort of separated them out, and it's very easy for the algorithm to actually find a separation between those two. So it's able to say that these 3 belong together, and these 4 belong together, and that's your two clusters, the 5, 6, and 7, and the rest. So it sort of seems to be doing the right thing, right? And that's the advantage of the spectral method, is that it can also do. You can not only do graphs, you can do non-linear clustering. So it's able to detect, if you have a data set like a circle, right? So there's a cluster here, and maybe there is another set of points out here. Maybe that's another cluster. So basically this is one cluster, and this is another cluster. So it's actually able to, the spectral method, you can do exactly the same thing, just compute some sort of a similarity between the points, and then apply the what we just did. So it's able to separate the inner circle from the outer circle automatically. You don't have to build in any other assumption into the algorithm. So the spectral method can be used not only for graphs, it can be used for non-linear clustering in general. You just have to come up with the right similarity metric. So depending on the similarity metric, it will do different things. Okay, so now we are going to talk about another clustering, and this is the Markov chain cluster. And this, instead of using the Laplacian, this will be actually built on top of the Markov matrix, the transition matrix. So this is so the approach is as follows. So let me first give you the intuition, and then we'll go and talk about the details of the algorithm. So this method says, I'm basically going to do a random walk in the graph. Okay. Now we know for a fact that if we just do a random walk, we know that this matrix M is the transition matrix for a one-step walk. Right? So it tells you the probability of jumping from one node to every other node. If you want to do a two-step walk, so you want to say so in other words, if you say I start at a vertex U, and this matrix M tells me obviously the probability of ending up in any other node in one half, right? So let's say x1, x2, x3, x4. So the matrix M is precisely the set of transitions. And I can also have a self-proof. So I can say I can choose to remain at my own node, or I can choose to go somewhere else. So the matrix M is precisely this matrix. What is the probability of remaining in that node? What is the probability of transitioning to 1, to 2, to 3, to 4? Now the interesting thing is that the two-step walk, so if I ask, okay, what would happen in 2 steps? What would be the probability that, and these ways are connected, and this may have another neighbor, this might be connected to that. So now I'm asking, okay, what would happen, so let's make that x5. So now I want to know the complete transition matrix, okay? What would happen after 2 steps? What is the probability that starting from U, I end up in x1, I end up in x2, x3, x4, even x5, right? Because in 2 steps I can now also be in x5. So whereas the transition here would be initially 0, right? You cannot go from U to x5 in 1 step. So the transition probability from U to x5 is 0. But in 2 steps it has a probability. So what is the transition matrix for a 2-step Markov chain or a 2-step random walk? It's just actually M squared. If you just take the matrix M and multiply it, you can see that it will be the 2 steps, because the way the probabilities add up, it's precisely, right? So the only way to get to x5 is you either go from U1 to x3, U1 to x2 to x5. Or, so that will be the 2-step, approach. So you basically multiply the probability on this edge with that edge, and that multiplication will give you the 2-step probability. So it just turns out to be the square of the matrix. So in general, one can actually ask, what will happen after 3 steps? So if I do a random walk and I basically expand from you and I go 3 hops away, and now you're making a statement about the entire graph. You're saying what would happen, what is the probability that I would be at that node, right, in these steps. And this, obviously, everything must add up to 1. So it will still remain a transition matrix, and that turns out to be simply m to the power t. So that's a very interesting, nice result, that I can get longer and longer walks. All I have to just do is, and I can get longer and longer transition matrices by simply taking the powers. Okay, but unfortunately, if you do this, and you do the, so this will end up basically being like the page rank approach. You basically converge to the dominant, if you compute the eigenvectors, it will always converge to the dominant eigenvector. So it's nothing, that's not what we want, because we want to get the clusters out of that. And the dominant eigenvector by itself is not sufficient to get you the clusters. It just tells you which nodes are important, but it doesn't tell you the clusters. So what we're going to do is we're going to modify our walk in a slight variation. We'll say, okay, what I'm going to do is I'm going to walk 1 step, and then I'm going to somehow manipulate my transitions. Okay? And what I want to do is I want to basically make sure that the chance of staying within the cluster is higher, and the chance of escaping the cluster gets lower. Okay, so what we do is we do so the idea is that you do what is known as an expansion or a 1-step walk. So this MCL or the Markov chain clustering has basically 2 steps. It has an expansion phase.
Excuse me for just a second.
Yeah.
When you said end state,
It will remain a probability. Yeah. Every row will add up to 1. I mean, and you can do this basically by, actually if you expand it out and you do the matrix multiplication, you will see that it will remain a transition matrix. Yes. So the expansion by 1 step. And then the second thing is you do what is known as inflation. So this is basically saying enhance high probabilities and basically decrease low probability. So this I'll explain this more. But the basic idea is that it's not just any random walk, it's a biased walk. You walk, then you do some manipulation, and then you walk again. So the idea is to basically sort of exponentially cut off, longer and longer walk. So you don't want to go too far. Because if you venture too far from the starting point, that means you may be in another cluster. So you want to remain within the same cluster, and you want to increase the chance of remaining in the same cluster. And what happens at the end of this process is that you keep on repeating these 2 things. You basically walk 1 step, you do this bias thing, and then you walk another step and you do a bias thing, you walk another step and you do the bias thing. One can show that this matrix, as I'll show, will also converge to something. And then from that matrix, it becomes very easy to extract the clusters. And they become the Markov, chain clusters. So basically, the first part we already know. Like I said, if you do not have the inflation part, if you're just doing a random walk, and you compute the eigenvector of the transpose, it will converge to the dominant eigenvector, just like page rank does. So that part we know, and that's not very interesting. So this is the Markov chain clustering. This is the inflation part. So what really matters is the inflation. Now this formula looks like a pretty hairy looking formula, but it's actually very simple. So let me just illustrate this very quickly. What inflation is. So let me show you what we want to do. So let me make a very simple, like a 3x3 matrix. So let's just say that we have 3 nodes, and every node is of course connected to itself. Don't need that. Okay, and let's just make a matrix. So this is basically 1, 2, and 3. 1, 2, and 3. So let's just say that the chance of remaining at 1 is high. The chance of going to those 2 is just simple. 2, let's just say the chance of remaining is not that high. and it may go to 1 with 0.3, it may go to 3 with 0.2 probability, and the third one, let's just say that the chance of remaining at your point is even lower, and it has, I don't know, maybe it has propensity for 1, so let's just make it 0.5 and make that 0.4. So it's a Markov matrix, right? All the rows add up to 1. What else? Right. So I wanted to explain the inflation part, right? So I would have to square this, but I just wanted to show you the idea of inflation. So if you take any matrix, okay, just assume that this is the matrix M squared. That is, after 2 steps, this is what it looks like. Okay. Then the question is that you want to inflate this matrix. So whatever this matrix is, it's a transition matrix, and you want to inflate it. So the idea is that you take a parameter R. Okay, so this is called the inflation parameter. And R is basically greater than 1. So the idea is that you're going to take the R power of each entry. Okay, so for example, let me just do it with R equal to 2. So for example, if R equal to 2, then what you do is you take a vector. So you want to know, okay, what is the transition from 1, right, to itself? 1, 2, and 3. So initially, without the inflation, it's 0.8, 0.1, 0.1, right? After the inflation, what happens is I'm going to use the second power. So I'm going to square every entry. So this will become 0.64, 0.01, 0.01. And now you have a vector of values, but now you have to normalize it because I have to make it again into a transition matrix. So we add them up. The sum of all of these is basically 0.66, right? And so if I now divide, so because so first you do the inflation, you take the square of all the entries, and now you basically, so first you take the square, so raise to power R, and then you normalize. So after you normalize, it becomes 0.64 divided by 0.66, 0.01 divided by 0.66, 0.01 divided by 0.66. So what is the net effect? I don't know the exact numbers here. I mean, probably you can do the math quickly, better than I can. But let's say it's 0.95, okay? This is the 0. I'm just making this up, but it's definitely going to be. So essentially, if you look at this number and this number, the probability that was high gets even bumped up even higher, and the probability that were actually this is probably lower than that. So it's probably going to be 0.99 or something. 0.96. Yes. And what about these? So it's 0.02, 0.02.
0.02.
Okay. Anyway, so the point is that the higher transition probabilities get amplified even more, and relatively speaking, those guys get, demoted. So, and in fact, sorry, I'm sorry, you should have compared this with this one, not with this. So these were the initial probabilities, right? So 0.8, 0.1, 0.1, and after the inflation, the 0.8 has jumped to 0.96. The 0.1 has become, it has become even less. So this is the bias in the walk. So you sort of inflate high things, you decrease the low things, and this is how the method. So this becomes the parameter of the algorithm. Okay, so whether you wanted to take a square or a cube, or maybe something lower, maybe 1.5, that is not clear what the right value should be. So this method does not use the K. It does not ask you how many clusters you want to find. It just says what inflation parameter you want to use. And different inflation parameters will give you different clusters. And the higher the parameter, right, the more the inflation, the more the skew. The walk will not proceed very far because you have more chance of sticking very local. So that means it will find lots of small clusters. Right? So high value of R means you don't walk very far, you get very small clusters, but you get many, many, many small clusters. But if you pick a low value of R, let's say close to 1, 1.1, 1.2, 1.5, that means you can walk further and further away in the graph. So you can get larger clusters, but you will get fewer clusters. So anyway, so here's the basic algorithm. This is called the Markov chain clustering, and you can see it's very, very simple to implement. You start with your adjacency matrix, and you have to add the self loop. This method only works if you have self loops. Okay? So it has to be a proper transition matrix where you have the probability of staying at your own node also. And then you just compute the Markov matrix, the one-step transition matrix. And now it's just a series of these steps, right? So the step size is going up one each time. Every time I first compute one extra step, right? So when I multiply the transition matrix by itself, I get the two-step matrix. So it's like taking one extra step. So that's the expansion part. And this gamma notation, I'm basically saying that with the parameter r is the inflation. Okay, square it and then normalize it, or take the rth power and then normalize it. So do the inflation. And then keep on doing this till the transition matrix doesn't change. So one can show, and this is a proof, which is a very lengthy proof, because it's a little bit harder to show that in a biased walk it converges. One can actually prove that this matrix actually converges to a matrix. And now once you have this converged matrix, it turns out it's very easy to extract the clusters from that. The bottom line is that you can basically look for connected components, because this matrix you can extract like a directed graph out of it. And the connected components, the weakly connected components, turn out to be the clusters. So I will not go through those, but let me just show you an example here, which let me see if I have it. Actually, I don't think I have the matrix here. But anyway, at least I can illustrate what happens on that example network. So if you run the method through, you get this converged matrix, this inflation expansion matrix, and then the directed graph that pops out of that, it actually converges to this directed graph. It basically has, just take this graph and make it into an adjacency matrix, and you'll have the corresponding, what it converged to. This is just a faithful representation of that converged matrix. So this says that vertex 3 has an entry to 4, 2 has an entry to 4, 1 has an entry to 4, and they have values 1. And this 5 gets, is directed to 6 and 7 with this kind of, value in that matrix. And this is the actual graph of that matrix, okay, a directed graph of that matrix. And essentially the connected components, so this goes back to my, the last part. The first, from this matrix, you create this, you create this graph. Okay, so the matrix basically tells you what the graph will look like. Okay, and when I do the actual, when we do the hands-on thing, we'll probably do an example of this one. And then you just have to pick up the connected components. Because it's a directed graph, you have to say weakly, because it's not a strongly connected component. So this is what the graph looks like. And this graph has basically two components. One component here, one component here. And those are your two clusters. So again, it is able to separate, the 1, 2, 3, 4 from the 5, 6, 7. The only thing I would say here is that these gray nodes, they act like, they're called attractors, okay, in this. So in a way, the 1, 2, and 3, sort of their influence or their flow gets sort of accumulated at 4. So 4 is kind of like a representative of that cluster. Okay? And in this, because 5 can be equally 6 to 7, so actually both 6 and 7 happen to be representatives, and 5 gets attracted to both of them. And so, but nevertheless, they still make up one component. So there are two components. So in this case, I'm not sure what inflation parameter I used. I may have used R2 or it's written? Oh, R2.5, okay. So remember, this is important. I mean, just to show the thing, I said, okay, if I choose this value, I'll get these two. But if I choose a very low value, maybe everything will end up in the same cluster. And if I pick an even higher value, you might get further, splits. So in this case, you just have to choose the parameter. You don't know how many clusters will end up coming out of it. So you have to sort of play with it. So that's the Markov chain clustering idea. Alright, so I think we have done the things we wanted to cover, right? So we take a break for 15 minutes? 30-minute break, and then the tutorial.
There is tea break now.
Tea break.